Good morning. This is Ed Laturco with the Lexington Veterans Association. Today we're going to have a special presentation done that was once done before, but we had a few glitches, and we're getting by that by bringing our speaker back again to pretty much capture, because it was such an important and very successful program that we did back in June of this year. Max, in August 1945, following the surrender of the Imperial Japan, U.S. Navy submarine force was the world's largest. However, at the end of World War II, the famous Silent Service, with its major opponents defeated, was an underwater fleet that had lost all rationale for its existence. In the post-war years, the U.S. diesel submarine force, based on now obsolete technologies, languished and dwindled in size as no foreseeable naval foe could justify its upkeep and maintenance. But with the start of the Cold War and the determination of the USSR to challenge American power globally, including at sea, a new significant threat suddenly arose. The Soviets began building large numbers of submarines based on advanced U-boat technologies that Allies had captured from the Germans. The U.S. did have a political will to match the Soviets hull for hull. However, tremendous possibilities of nuclear power, an American advantage, promised to give the U.S. Navy technician superiority over the Soviets. The development of nuclear-powered warships was a result of hard-driving officer, a genius named Hyman Rickover, whose single-minded passion for nuclear energy and the creation of culture of excellence kept the United States Navy the dominant maritime power over the past 60 years. Maxima Holland will represent the history of the United States Navy's nuclear attack fleet from its early days in 1950s and up until the present day, detailing the designs and technical developments, innovations, successes, and failures along the way, chronicling undersea duel between the United States Navy and the Soviet Navy for supremacy on the world's oceans. Maxima Holland graduated from the United States Naval Academy with a degree in National Security Studies. During his 10 years of active service as a surface warfare officer, he chased Soviet submarines in the Atlantic, Pacific, and Mediterranean. He taught defense policy and naval strategy at the German Naval College for 2.5 years. Max has also published papers on naval diplomatic history. A Harvard MBA, Max today works as a strategy consultant to New England businesses. I'd like to introduce Maxima Holland as our speaker for today.
Well, thanks for the great introduction, Ed. Appreciate the kind words. Again, as I mentioned, my name is Maxima Holland, and I'm here to talk today about the evolution of the U.S. Navy attack submarine from the end of the Second World War to the present day. The word evolution is consciously chosen. Most people think a submarine is a submarine is a submarine. But in reality, over the last almost 60 years now, the Navy submarines have gone through a tremendous variety of changes, adaptations, innovations, and so forth to get to where they are today, sometimes making some tremendous breakthrough advances, sometimes making some missteps along the way, but all, again, based upon learning from mistakes and capitalizing on successes. So what we're going to talk about today is a little bit of the design history, technical innovations, strengths and weaknesses of different submarines over the last 60 years, knowing that each submarine class built upon the lessons learned from the previous one. We'll talk about the international responses because it's not a single case of the U.S. Navy alone. There is an opponent. There's a foe, which was mentioned, the Soviet Navy, as a real significant threat to the United States and also an operator of a substantial number of submarines, both conventional and nuclear. We'll talk about the competitive advantages and then basically really a stroll through 70 years nearly of where we got to today. I'm going to start with a quote from Admiral Rickover. As Ed had mentioned, he was the driving force for the adaptation of nuclear power. And his quote is, "The nuclear-powered submarine is not just an improved submarine, it is a totally different kind of warship." And that's, again, based upon the advantages it had of being independent from the Air Force engines and being able to operate almost indefinitely beneath the oceans, where its stealth capabilities gave it tremendous advantages over previous types of submarines. And we'll talk about that some more. I have a lot of slides. We're going to go through these at a relatively quick pace, so you have to bear with me. I'll try to keep my talk at an understandable cadence. But there's a lot of words. I'm just going to touch on the highlights. You can then look at the slides and to your own pace read the additional commentary. First, we're going to start off with a quick primer on Navy nuclear power plant nomenclature. Each reactor plant is a letter-number-letter combination. The first letter is the type of vessel that it's on, so we're going to talk about S. So for submarine, there's A for aircraft carrier and C for cruiser and so forth, but we're going to deal with the S. The second is the number is the generation. So where along the line in the development from the first generation to the current one does this stand? And then the last letter is for the reactor's designer. And those are almost overwhelmingly going to be either W for Westinghouse or G for General Electric. So as an example, an S8G reactor is a submarine reactor, 8th generation, made by General Electric. You're going to hear me say about S1C, S2W, S5W along the way. That's what it means. A submarine reactor, where along the development path it is, and then who the maker is. And that's the type of terminology that the Navy uses all the time. So going back to what Ed mentioned, at the end of the Second World War, the U.S. Navy had the largest submarine force in the world after the defeat of the Japanese and the Germans. In 3 years of a nonstop combat in the Pacific Ocean, the U.S. Navy basically cleared the oceans of Japanese warships and commercial vessels, driving Japan basically to near collapse because of its economy. It was unable to be resupplied with all of the raw materials it needed to keep in operation. But when the shooting stopped, the U.S. Navy submarine force was technically obsolete. Now, the U.S. Navy had nearly 150 of these really large, fast, heavily armed submarines of the three classes, the Gato, Baleo, and Tench, that could operate the entire width and breadth of the Pacific Ocean. But at the same time, they were, at this point now, technically obsolete. Even though they were fast and were able to carry, again, a large torpedo loadout, as most submarines at that time in world history, they operated 95% of the time on the surface, which made them vulnerable to air attack. That was the reason for the Germans losing the Battle of the Atlantic in World War II, was that the overwhelming Allied air power sank hundreds of German submarines over the course of the 6-year Battle of the Atlantic. So even though we had this large fleet of relatively recently built submarines, most of them were less than 2 years old, in reality, they were almost all, again, technologically obsolete. And the reason for that is that in the very last year of the war, the Germans had been building what's called an electro boat, or the Type 21 submarine, which was really designed not for operating on the surface, but really operating beneath the surface. They were fast also, had a tremendous range. They were stealthy, they were hydrodynamically streamlined to actually operate faster underwater than on the surface. They had tremendous battery power. They could outrun ships underwater, which was the first time that had ever been accomplished. And so they had created lots of technical innovations and introduced them, including the snorkel, which allowed them to operate their diesel engines underwater while staying submerged. But again, the reality is that these technologies showed up, for goodness sake, too late to change the direction of the war in the Atlantic Ocean, but they were still there and in development. After the war, the Allies decided that the remaining Type 21 boats would be divided up among the different powers to learn what the Germans had been doing and to adapt some of the technologies that the Germans had just introduced. Now, the Russians were particularly eager, more than the British, the French, or the Americans, to get their hands on this technology. Stalin was planning on expanding the Soviet Navy. He had been tremendously impressed at the ability of the Germans to nearly cut off North America from Europe and basically win the war from 1930 to 1945 through the submarine war. And so he wanted to get his hands on, and pretty quickly, once the Russians did, they started immediately redesigning or designing new classes of submarines based upon the captured German technology. However, the U.S. Navy, in the meantime, really without a threat, there was no naval opponent that was anywhere near the size of the United States, and those that were our allies, like the Royal Navy as an example. And so the U.S. Navy submarine fleet was basically a poor stepchild of the rest of the U.S. Navy, which was based on aircraft carriers and carrier battle groups. And since without any particular threat, they were basically given just the minimal amount of funds to maintain their fleet. So in 1946, after the war had ended and we had developed the atomic bomb, the U.S. decided that there was opportunities to explore other uses for atomic energy other than for explosives. And one was a nuclear power plant to produce electricity. And at Oak Ridge National Laboratory, which was the site of one of our largest enrichment facilities and also a design facility, they pulled together a study group to look into that matter. The U.S. Navy sent 8 people to take part, one of whom was a gentleman named Captain Hyman Rickover. Now, Rickover was a career engineering officer. He'd spent his time in the electrical branch trying to figure out how to make ships more survivable in combat based upon their electrical generating distribution plant, but he immediately recognized the advantages and the potential revolutionary aspects of nuclear power for naval warfare, specifically when it comes to propelling a submarine, as we mentioned before, indefinitely underwater without having to surface and expose itself to potential enemy air attack. In 1949, Rickover took over the control of the Navy's efforts as a director of naval reactors, which was a small group of probably about 10 people at the largest. But over the next few years, very quickly, was able then to expand that and drive support both politically as well as in Congress as well as in the Navy for the study and development of a Navy nuclear power plant for submarines. Now, Rickover has gone into the history books as the father of the nuclear Navy. He served in that role from 1949 until 1982. So every time that he had been up for promotion, the Navy kept ensuring, or Congress kept making sure that he was going to receive another star. And over the course of over 50 years, or nearly 50 years in uniform, he basically created, through single-willed hard work and effort, the Navy nuclear power program. Now, no one ever built a submarine powered by a nuclear reactor beforehand. So they decided to do a safe strategy of doing concurrent design, meaning they would develop and design the power plant and the submarine simultaneously, and they would develop a submarine plant on land first just to prove it out. And this was the S1W reactor, which was created in a specific facility in National Reactor Testing Station in Idaho. Idaho is a desert location. If there were any accidents, so forth, and spread of radiation, there weren't many people nearby. It was considered to have been a location to do that. Now, to really make sure that the submarine could support a nuclear power plant, they built the reactor in a mock submarine hull and put that mock submarine hull in a tank of water to give it the most realistic types of conditions. Now, the result then was the development of a reliable and compact nuclear reactor in a very narrow submarine hull. But they had to overcome tremendous amounts of unknowns in terms of engineering. No one had ever built a nuclear power plant to produce power, to turn a screw, to create steam, to drive a turbine before. And so reactor operating bases, materials of construction, design aspects of and so forth were all done on the fly, so to speak. But they were successful in their development. And the first submarine to contain a nuclear power plant was the Uss Nautilus. It was launched at Electric Boat here in Connecticut in 1952, and just a few years later was operating underway on nuclear power when she put to sea and electrified the world with her radio announcement. Now, Nautilus was relatively conventional from a ship naval architectural aspect. She was really just an enlarged World War II type submarine, twin screw. Didn't have a lot of aspects necessarily what the German Type 21 had, but her power plant was unique in that she could, again, operate underwater indefinitely without coming to the surface. During the time that she was operating the first few years, she broke almost every record that submarines had beforehand, including traveling, under the North Pole, which just happened here in 1958, last week or 2 weeks ago, so the 60th anniversary. And in the course of trials, tests, and war games, she was able to show that the submarine was vastly superior to any warship on the planet. But she was altogether a relatively inefficiently designed submarine. Again, as I mentioned before, she was not particularly well streamlined, was relatively noisy when underwater, especially at high speed, but she could steam at high speed, 23 knots, which was faster than many escorts could operate at that time. Now, Rickover was a restless engineer. He was always looking for a new and better way of doing things, at the same time that the pressurized water reactor, which powered Nautilus and subsequently almost every other submarine. And to contain this reactor, a submarine was then built, the Uss Sea Wolf, which was the first of its kind, much more technologically advanced, this liquid metal cooled reactor plant. But there were a lot of technical aspects and some challenges in terms of operating this kind of temperamental reactor plant. And so because of some safety hazards dealing with the liquid sodium in a submarine underwater, liquid sodium will explode upon contact with water, decided that this was really a dead end, despite the fact that on paper it was a tremendous advancement, that in reality that it had also some serious limitations. And so the S2G reactor plant was then ultimately replaced by traditional S2W, the same kind that was in Nautilus. Now, During the time that these two submarines were now in operation, as I mentioned, they were going through lots of trials and tests to see what they could do. And again, it came up to the realization among many senior officers, all the way up to the Chief of Naval Operations, that these submarines were really vastly greater than anything, that they were equal to multiple numbers of a conventional submarine because of their stealth, their ability to travel at high speed, and they had been able to successfully intercept and attack carrier battle groups, which again created a lot of great concern among the U.S. Navy leadership, especially if the Russians were thinking of something similar. But they weren't at this point. However, around the same time period, in the 1950s, Premier Khrushchev decided that what he wanted to do was challenge the United States militarily across the planet, not only in terms of building rockets and nuclear weaponry, but also in terms of challenging the U.S. Navy's control of the seas. And he instituted an enormous, massive naval buildup, including large numbers of submarines, missiles, and nuclear weapons. And he put in place an admiral that was very similar in several ways to Admiral Rickover. These were hard-charging, temperamental, profane, kind of people that brooked no opposition and really were perfectionists. And that was named Admiral Gorshkov, who was today considered the Russian Rickover. So now that the U.S. had built two, they were one of a kind. They were all basically custom made. They decided that the next step is to try a small class of multiple submarines to see if the industrial base could produce multiple sets of equipment for the power plant. And these were the Skate class, introduced in 1955. The last one commissioned in 1959, and they were basically improved layouts of the Nautilus. They were better streamlined. They found out where noise generation was taking place, and then it made them faster and also made them quieter. So one of the famous things of Skate was surfacing at the North Pole in 1959. Nautilus had sailed under the North Pole in 1958, but this was another propaganda or public relations coup on the part of the United States. As I mentioned, Skates were basically improved Nautiluses. They took the lessons learned from operating the first submarine and then tried to improve them. The Skates were in service for a long time, from the 1950s until the mid-1980s, but they did show that the U.S. industrial base could manufacture these types of equipment in quantity. They were built in 3 different shipyards as a way of not only dispersing the industrial base, but at the same time also of training shipyards, multiple shipyards in different parts of the country, in the assembly and manufacturing of nuclear submarines. So in the meantime, while the U.S. was building the Skate class, the Russians immediately jumped into their first submarine class called the November class. They didn't do any first of a kind. And I should say that neither Nautilus nor Sea Wolf were prototypes. According to Rickover, none of the submarines that he built were prototypes. They were all combat submarines. They may prototype different types of technologies and approaches and design, but they were all combat submarines. They weren't simply for testing alone. They were developing new technologies, but they were intended to be warfighting ships at the same time. The Russians went straight from 0 to 60 miles an hour. They produced the November class, a large number of submarines. They were incredibly fast. They had twin reactors on board, twin propellers. They were very, very fast at over 30 knots. But at the same time, which was a tremendous advancement to go from nothing to a 30-knot submarine. But they were known as widowmakers. They were poorly built. They had shoddy designs and aspects. They had a lot of manufacturing defects. They were built under bad conditions in shipyards in the Soviet far north, where weather conditions weren't necessarily the best. And so they ended up with several of these submarines experiencing fires, explosions. Several sank due to accidents on board and so forth. So they tried, they bet big, but they took a risk. Now at the same time that they're introducing the first of the November class submarines, the Soviets were nonstop building conventional. These are diesel-electric submarines in huge quantities. So the Whiskey class, 238 built, Zulus 26, Quebecs 30, you can see the numbers here. That caused incredible amount of anxiety among senior naval officers, both in the U.S. and in the Royal Navy, because we remembered very clearly, just only 10 years earlier, the proximity the Germans had to winning the war by cutting off North America from Europe and keeping our forces fighting in Europe from being resupplied. So knowing that the Russians were building this massive amount of diesel-electric submarines gave concern that what the Russians were trying to do is prepare for World War III. And that meant, however, that the U.S. Navy had to respond. But we didn't have the political will to build large quantities of submarines in peacetime. So that meant that instead we decided to go and look at quality over quantity and combat them that way. Now, while we're doing different types of reactor plants, pressurized water, liquid sodium, we're also looking at different types of hull forms. And one of these was this is a true prototype submarine. It was an unarmed
diesel-electric experimental submarine that had a very unusual hull type. It was basically rounded submarines, not like a deck on the top, or not looking like a World War II submarine, but really looking more like a fish. And this was the Uss Albacore. She pioneered, it was called a teardrop hull, I'll show a picture in just a moment, and a single propeller. So going away from double propeller, going to a single propeller, having an incredibly streamlined, very, very slippery hull. And looking at that in terms of speed, and it showed tremendous capabilities. So after the Skates, the next class was the Skipjack Class, which married the streamlined Albacore hull with a new and more powerful S-5W nuclear plant. S-5W was, at its introduction, a breakthrough in terms of power output, ease of operation, ability to maintain, and so forth, and married these two. This brand new high-powered power plant, a very streamlined hull, advanced steel manufacturing, HY-80, means it could dive incredibly deep, a multi-bladed propeller. So the result was that the Skipjack Class was the fastest, deepest diving submarines on the planet. And they operated this very reliable and highly rugged S-5W plant. This combination of nuclear power plants, teardrop hull, single propeller, multi-bladed propeller blade, became the standard template, basically, for future U.S. Navy submarine design that exists to this day. Now, what does a teardrop hull call it? Also the body of continuous revolution. It's, if you look at some high-speed fish, such as the skipjack tuna, which is where it was named after, it has a very long tapered hull, starts narrow, broadens out, and then tapers to a tail. And if you look at the picture of the submarine beneath that, it has a very similar design concept. So we looked at nature, what nature does underwater, and adapted that as well. So they were very successful submarines, as I mentioned before, fast, maneuverable, deep diving. But one of the problems was this continually tapered hull meant that it was very cramped inside. There wasn't a lot of room, excuse me, or ability to modernize, upgrade, or change out additional equipment. So they were relatively space limited, but they could do 32 knots, was the fastest on the planet at that time. And overall, they were very popular, very successful, considered race cars of the deep by their crews because they could outrun anything basically underwater and outrun most surface ships as well at the time. Now, the next submarine attempt was the USS Triton, which if you're in your 40s, 50s, and 60s or older, you may have heard about as doing the first submerged underwater trip around the planet. The Triton was a radar picket submarine based upon experience at Okinawa in 1945 when dozens of our destroyers were hit by Japanese kamikazes. The thought was that rather than having a destroyer excuse me, doing air support or air detection, we'd have a submarine that would surface in front of a battle group or in front of an invasion fleet. It would then survey the airspace around it. In the event of an attack, it would submerge and avoid kamikaze attack. The problem was, though, that the amount of time it took to raise the radar and lower the radar and then submerge was too long, especially in the era of supersonic weaponry and fast-flying aircraft and so forth. So the radar picket concept for U.S. Navy submarines was really a dead end. And also she was a twin propeller, twin reactor, and the fact was that she had an enormous crew that just made it not economical to operate. So even though they took away the radars, turned it to an attack submarine, realized that the costs of operating this one really big white elephant, so to speak, was not worthwhile, and she was eventually mothballed in the 1960s after about 10 years of service. So that was one of the rare failures in terms of submarine development. Now, the Nautilus, Sea Wolf, the Skate, Triton, and Skipjack classes were the first generation of nuclear submarines. They'd shown, again, the capabilities of what the classes could do. And so at this point now, we became looking towards gearing up and starting to produce nuclear submarines in large quantities to make up for, again, the Soviet surge in diesel-electric submarines. We needed to build at least one nuclear submarine for every 6 to 8 diesel-electric submarines to give us a chance of winning in the event of a war in the North Atlantic. But some new design features that became critical to optimizing were quieter power plants, thank you, improved sonars to be able to detect enemy submarines, deeper diving capability, and then also newer weapons, so beyond simply the torpedo. Now, again, taking one more aside, Rickover decided to build a one-off submarine, one of a kind. It's not a prototype, though. It was an operating submarine, USS Tullabee. She was a test bed to try out a couple different things, evaluating deep diving, ultra-quiet submarine. And she had some new design alternatives that, again, became really quickly par for the course in terms of future submarines. First of all, she had a spherical sonar array, so the entire front end of the submarine now had a very large low frequency. And why is low frequency important? Because that allows you to have much greater range. So she could hear and detect submarines at much, much greater ranges than any other submarine. Because the bow was now full of this big sonar system, the torpedo tubes, which in most submarines or in the bow, had to be relocated. They were moved aft and in midships and out at and angled at a side, which was, again, a tremendous change from previous practice. And then lastly, she had a turbo-electric power plant, meaning rather than being powered by steam turbines, she had electric motors. So a reactor plant turning a steam turbine, which powered electricity to make electric motors instead. Tullabee, again, her systems, her sensors, her layouts, her combat systems were the pattern for all subsequent attack submarines. And as you can see, also, she had a teardrop hull with a single propeller that the Skates first had. I'm sorry, the Skipjacks first had. But she was never intended to be a mass-produced submarine. It got a lot of criticism for being small and slow, but she was also at the same time the world's quietest submarine by far and was able to dominate in all combats, even against our best nuclear-powered submarines. But at 16 knots, this was not something that a submarine would be able to achieve long-term, especially if the submarines, after detecting her, could run away. But it was an attempt. It showed that the turbo-electric drive and this new bow sonar system was a great approach. So the next class of submarines were the Thrushes. These were the first attempt to build now large class, meaning 20-plus submarines of a single design, incorporating all of the technology advances, innovations that were done beforehand, incorporating the S5W reactor, the teardrop hull, as I mentioned, single propeller, angled torpedo tubes, large bow sonar, in a single submarine. Also carried a new weapon called the Subrock. This was basically a rocket-launched nuclear depth charge. So we have this long-range sonar that can detect submarines at miles and miles away. One of the things, rather than actually the outer torpedo range, what you would do is shoot a missile that would exit the torpedo tube, fly through the sky, and then drop a nuclear depth charge on top of the enemy submarines. There's a picture here of the bow-mounted sonar, which was, again, a tremendous technological advancement. It was a wonder of the era in terms of its ability. Now, the Thrushes were bigger. They realized that the Skipjacks were too cramped, so the Thrushes were built from the beginning to allow updates and modifications. And again, were considered to be a fantastic leap forward in terms of incorporating all these new things. However, one of the problems was that with the same S5W reactor that the previous two submarine classes and being substantially larger, result is that her speed was down to 27 knots now. So while the Skipjack could do 32 knots, the Thrushes were down to 27 knots. Now they tried some things to get around this by cutting down the size of the sail, but the result was, again, made them relatively unstable or hard to handle at shallow depths. But this is a comparison side by side of the Skipjack at the top and then the Thrusher at the bottom to scale. As you can see, new submarine is much larger, much roomier, broader hull for a lot longer portion of the hull length. And so, again, it married all these concepts into a fast, maneuverable submarine design. The U.S. Navy was thrilled, seemed to satisfy every goal, and we started mass production of these submarine classes, the Thrushes, around the country. But 1963, in April, disaster struck. The Thrusher had just gone through a short maintenance period at Portsmouth Naval Shipyard, New Hampshire, was just doing a routine test dive off of Cape Cod when she ran into trouble, ended up then sinking. She was crushed by ocean depths. The accident investigation was undertaken, found out that there was a leak excuse me, in one of the saltwater piping systems. It was a silver braze joint that caused that gave way, that inundated a power panel that shorted out, that caused the reactor scram, and then the reactor, without power, basically the submarine then sank to crush depth and was destroyed along with her entire crew, and also 19 shipyard workers who were riding on board just to see how things were going. So one of the problems was that at this time there were already 14 of the Thrusher classes in operation or under construction at this point. And so it caused an immediate halt to all manufacturing for a substantial amount of time, over a year. All the submarines that were in service had to be brought back to the shipyard. All the silver braze joints had to be replaced with welded joints. All the submarines that were under construction had to be suspended construction as well to make those improvements. The designs had to be updated, modified. And the Navy introduced what's called the Sub-Safe program, which was really the most rigorous quality approach, looking at every aspect of a submarine that could cause a potential failure. And so to this day, the U.S. Navy builds all submarines to the SubSafe program, which is far greater in terms of its stringency than the NRC for nuclear power plants or the FDA in terms of food quality manufacturing. Navy submarines are probably built better than almost anything built today, FAA in terms of airline certification. Here's some pictures of Thrusher. She was eventually found, and then a submarine, a little mini sub, unmanned, was sent down to take pictures, but they were never able to determine anything other than the reactor shutdown. Things that nuclear submarines operate at a negative buoyancy point. Excuse me. Negative buoyancy, which means that they naturally will sink if they lose all power, and that's what happened to Thrusher. So to keep at their operating depth, they have to keep powered continuously, and that allows them to get to the surface as well. Once Thrusher went down, the Navy, being composed of sailors, many of whom are superstitious, renamed the entire class from Thrusher Class to Permit Class, which is the second submarine of the type, put all kinds of improvements in place, again, pulled the ones out of service that were operating, stopped construction of the ones that were doing. And then lastly, the last three submarines were then improved. They stretched the hull to give it greater stability at shallow depths, gave them more powerful engines as well. And but by doing that, making the submarines even larger and even heavier with the same S5W power plant, they became even slower. Now they're 7 knots slower than the Skipjack, so they're at 25 knots. Another one-of-a-kind submarine, again, not a prototype, but one-of-a-kind, USS Narwhal. This had the S5G natural circulation reactor. The most noisy single item on a submarine is the reactor coolant pumps. Those are the ones that keep the primary loop flowing and keep the reactor cool. Why? Because reactors need to have thousands of gallons of cool water poured through them constantly to be able to stay cool and not melt down, because the energy is, again, so fiendishly hot. And so the reactor coolant pumps are the single largest source of radiated noise from a submarine. So the S5G's natural circulation reactor allows a reactor power plant to operate without reactor coolant pumps. And this allowed the Narwhal to be, again, the most silent submarine to date. Now, that's a low power. She could operate in natural circulation, turns her engines off, or her circulating pumps off, and simply because hot water rises and cool water falls, it causes a natural loop that can cool a reactor. But she was at 26 knots, one of a kind, but had a lot of promise to it. So the Sturgeon Class was the next class after the Permits, former Thrusher class, and these, again, incorporated significant design improvements. In many ways, they were improved Thrusher/Permit types, but they overcame the design compromises that had been put into place beforehand. They were bigger than the Permits. They were even wider. They carried more powerful bar sonars, improved engines. They got a taller sail for handling and control, better periscopes, sensors, and systems. Basically, it was in every single aspect of propulsion, communications, and weapon systems, they were better. And again, Thrusher, ultimately, again, from just a perspective, they look very similar, and they do. But again, think about it as an enlarged type. We built 37 of the Sturgeon class between 63 and 75, and they were considered really the best submarines built to date at this time point. But because, again, they had S5W, that slowed them down to 26 knots, so that's not good. But they could carry the latest communications and electronic systems, which meant that they were used in lots of places where the submarines were not necessarily supposed to go. We did a lot of intelligence gathering operations, both off Murmansk in the northern part of Russia, as well as off of Vladivostok in the Soviet Far East. And these submarines had the capability of doing those kind of missions. So again, fast, quiet, carried electronics for secret surveillance and reconnaissance missions near enemy coasts. And they were basically the backbone of the U.S. Navy submarine force for 20 years. Okay, next one-of-a-kind submarine, the Glenard P. Lipscomb. Again, Rickover is not going to risk trying out some new technology and unproven technology on a class of submarine. He's going to build a one-of-a-kind submarine, see if it works, and then if it does, adapt it into future builds. So the Glenard P. Lipscomb emphasis was on machinery quieting, which meant that she had basically a single turbine without reduction gears. And reduction gears are the second most noisiest aspect of a submarine. First, there are coolant pumps that circulate water through the reactor, but then reduction gears, which reduces the speed of the high-speed turbines to the slower speed of the propeller. But they radiate a lot of noise. Well, the Glenard P. Lipscomb took away reduction gears, used different innovative engineering techniques, and it worked. She was really, really quiet, but even slower at 23 knots. And on May of 1968, so again 50 years ago, a couple months ago, the Skipjack, the lead ship of the Skipjack Class, disappeared in the North Atlantic while returning home from a mission. It took some time before we found her, but based upon some really tremendous sleuthing on the part of mathematicians and sonar technicians and so forth, we were able to find her localized in the Atlantic Ocean. Never found a definitive cause for her loss. All we could say that it was an onboard explosion. What caused the explosion, no one knows to this day. Now, while our submarines were getting bigger and at the same time slower, the Soviets were introducing their second generation of submarines. So they went from the November and realized that was a lot of shoddy manufacturing, poor design aspects, bad radiation protection, and so forth that caused their crews to shun them. They started to introduce the Victor class submarines, which had a very, again, teardrop hull, twin reactors, but also very, very streamlined, slippery, in many ways mirrored in terms of design, hull design, U.S. Navy submarine practice of that day. And they built 48 of these submarines over the course of about 20 years. They could do 32 knots. Now, again, these are a substantial improvement. As you can see, the pictures here of the two Victor class, Victor 1 and Victor 2 generation. Now, at the same time, they're also developing another generation of another class called the Charlie class that were intended to attack U.S. Navy aircraft carrier battle groups. So these weren't to sink our merchant convoys crossing the Atlantic. These weren't meant to sink our other submarines. They were intended specifically to knock out the carrier battle groups, which really the Soviet leadership feared after they saw what the U.S. Navy had done to mainland Japan in World War II. They realized the capabilities of carriers in terms of doing lots of damage. And then lastly, in the second generation of submarine class, the Russians came up with the Alpha class. Now, the Alpha class was the most streamlined submarine and also the fastest submarine ever built at over 40 knots. How do they do that? Well, they used the liquid metal technology that we had used way back when in the Sea Wolf and rejected as being too dangerous. Well, the Alpha class submarines, they built a handful of them, had very powerful reactor plants. They were very small submarines. They had an all-officer crew because they were so difficult to operate technically. They were considered to be interceptors. In the event of an approach of a U.S. Navy battle group to Soviet shorelines, they would send out the Alphas. They would storm forward at 40 knots, shoot the torpedoes, sink the aircraft carriers, and so forth. But while they were the fastest submarines ever built, they were also among the most dangerous. And there are stories, and I haven't heard any exact numbers, but I've been told that anywhere up to 3 of the Alpha-class submarines were either sunk or ended up having to be cut up and buried ashore because of the radiation contamination, including killing 1 or 2 complete crews because of problems that they encountered. So Alphas were also kind of a dead end, but from a technology perspective, very impressive. So like I say, difficult to operate because of tricky reactor plants, but very noisy as well. But they had amazing speed. So why is that important? Well, in the 1970s, the U.S. Navy realized that the Russians were aiming at U.S. Navy carrier groups. This was first realized, I think, 1972, when the USS Enterprise was transiting from Oahu to off the Vietnamese coastline for deployment, and was intercepted by Soviet nuclear attack submarines. And despite the abilities or the attempts of the U.S. Navy to operate at 30, 35 knots to escape, the Soviet submarine hung along and did not allow them to escape, which really caused a lot of anxiety and distress among the senior U.S. Navy officers. At that point, it came to the decision that what the U.S. Navy needed was a submarine escort to escort a carrier battle group to take on any Soviet submarines that were hounding them or chasing them or intended to attack them. The problem was that, with exception of the old Skipjack submarines, there wasn't a single U.S. Navy submarine operation to keep up with an aircraft carrier battle group, which routinely operated at 30 knots. As I mentioned, our submarines were getting bigger but slower because we were using this S5W reactor plant, which everybody loved, but at the same time had serious power limitations in terms of them. So it became obvious at this point that S5W was no longer going to be sufficient for future design generations, and that a new submarine and a new power plant would be needed. And that was the Los Angeles class, which is the third generation of submarines built. First one launched in 1976. They were, for 30-plus years now, the backbone of the U.S. Navy submarine fleet. They're now slowly being replaced. It was obsolete that we had, and so they started to replace them and decommission our older classes of submarines. This is a machinery raft. It's basically a sound isolation. The entire engine room basically is on this mounted system that was kept independent from the hull on these rubber grommets, so to speak, that make sure that the power plant vibrations weren't transmitted to the hull, which would then go into the ocean and allow them to be detected. As I mentioned, the newest sensors and weapon systems that carried vertical launch cruise missiles, in addition to, again, lots of new developments in terms of their digital fire control systems that use the most powerful commercial off-the-shelf computers around. And since they were so big and roomy, they could be upgraded. And that's why submarines built in the 70s, late 70s, early 80s, are still in operation today. Probably, well, maybe those ones are now going out of service and being replaced with the new Virginia class. But they were beautiful submarines. They were fast, thoroughbreds of the sea. But the Russians weren't standing still either. And so they were building bigger, faster, and newer submarines. This is a picture of the Oscar class submarine, which was a cruise missile firing submarine. The Russians built 13 of them. And they could, even though they're big, and like I say, they could still, because they had 2 reactor plants on board, they could still do 32 knots. Now, again, this is a picture. These are big submarines. They're really large, and I mean huge. But 32 knots, twin reactors. And in 1984, the Russians developed their own 3rd generation of nuclear attack submarine that was intended to go head-to-head with our Los Angeles class submarines. That was called the Akulas. Now, the Akulas were amazingly quiet. In fact, the first time that they went to sea and were trailed by a U.S. Navy submarine, which we did whenever they sent the submarines out, we would follow them, most of the time unknown to the Russians, although they suspected that we were there. If you've seen the movie Hunt for Red October, you know what that's about. But the Russians had used industrial espionage. They used Toshiba technologies in terms of their computer-controlled metal-cutting equipment to produce incredibly quiet machinery. Up to that point, they've been using Soviet-built machinery, which, again, has its defects and its limitations. But they went outside. They went to Japan and bought the latest metal-cutting equipment from the Japanese, which caused Toshiba actually to be banned from the United States for some years in terms of not being able to sell their equipment because of that as punishment. But they were very dangerous submarines. They were very capable. And according to many U.S. Navy officers, almost as capable as the U.S. Navy's Los Angeles class. So now that the Russians have a near-peer equivalent in the Akula, decided that the Los Angeles class might not be the last step. So the Navy then decided to build the most advanced submarine ever conceived, and that's the Sea Wolf. Not the old Sea Wolf, the liquid metal one, but the new Sea Wolf, the SSN-21. Had greater firepower than any submarine. She had 8 torpedo tubes instead of the 4 that was common for almost 50 years at that point. She was designed to fight and win World War III in the Atlantic and the Pacific Oceans. Now, it's supposed to build 29 originally, but when the Cold War came to an end in 1990-91, only 3 had been built, and at that point they came to realize that do we need a 35-knot submarine with 8 torpedo tubes when the Russian submarines to that port were now back in port and rusting pierside. And so even though they were, again, the most capable submarines, it says that they're 10 times as quiet as the Los Angeles class submarines. Only 3 were eventually built, the Sea Wolf, the follow-on Connecticut, and then the spy submarine Jimmy Carter, which has a separate 100-foot length hull section put in place to carry things. Multi-mission platform, basically recovery vehicles, mini submarines, all kinds of other things like that nature. No one really knows or can't say officially. So this is the spy boat Carter. Again, she's a little bit different, bigger, one of the longest submarines we ever had. But they were the most dominant submarine class. They were by far, again, intended to fight and win, dominate at sea. But with the collapse of the Soviet Union in '91 and the fact that the Russian Navy then also ended up decommissioning many of its submarines because of the economic crisis that was taking place at the time, Congress decided that these submarines were too expensive to build in quantity. So at over $3 billion per submarine, they decided that really wasn't a good investment and demanded that the Navy cease production. But again, either cease production or develop a new and less expensive submarine. And the Navy said, we can't allow submarine construction to stop. If we lose that industrial base and technology know-how, it'll be hard to recapture. So the Virginia class, which is the current submarine class, and that's the last one that's in operation today, is the newest class of submarine. These were built to replace the 688s, intended also to supplement the small number, the 3 of the Sea Wolf class submarine, but they're multi-mission submarines. So rather than just go out and be intended to fight Soviet submarines, which aren't out there anymore, Russian submarines, not the Soviet Union collapsed, they were designed to operate in the littorals. In other words, to support U.S. Navy missions in terms of the global war on terror back in the late 1990s and after 2001 attack, 9/11 attack, and be able to do things that other submarines had not been able to do. So This shows a comparison between the Los Angeles Sea Wolf and Virginia class. As you can see, the Sea Wolf is, again, the heaviest submarine. It's the widest submarine. It's the fastest submarine. Carries the most weapons. And the Virginia is kind of an intermediary. It's not as capable as the Sea Wolf, but it's more capable than the Los Angeles class submarine. So it really is an improvement over the Los Angeles, but not, again, intended to duplicate the Sea Wolf because that was not possible. So they're basically only 1.8 billion only, if you think about that, but it's not something that's considered to be a cheap submarine. These are not submarines that are less capable. In fact, they're more capable than Los Angeles submarines, so they are an improvement, although not, again, as capable as the Sea Wolves. To reduce their costs, they use a lot of commercial off-the-shelf components and computers and data networks, so they use Intel processors and other kinds of things that, because the development cycles in the civilian world are so much faster and the power capabilities are getting so much quicker than using military electronics. So they're built by 2 submarine shipyards. Originally, submarines were just built at Electric Boat in New London, Connecticut. But to be able to spread the wealth and keep the work base, they split the contract between Newport News facility in Virginia and Electric Boat in Connecticut. And they're built now in modules, so in sections that are then brought to a shipyard and welded together. So rather than the old style of building a hull and then stuffing it full of stuff similar to building a ship in a bottle, these are now built in components, sections, that are then sent by barge from Connecticut to Virginia, Virginia to Connecticut, where they're made. So here's a picture of what it looks like. This was a design concept that the Germans had pioneered in World War II when their shipyards were being destroyed by U.S. bombers, that they would build their submarines ashore inland. They would barge them down to the final assembly point and then put them together quickly. So rather than having them sit on a shipyard where they could be destroyed by bombs, they would be built in sections instead and just welded together at the last moment. So here's some pictures of the different modules, the bow sections. Here's one undergoing its final integration and assembly indoors. You say, wow, that's a little bit different than in a dry dock. Yep, they're built indoors in a very, very huge building. And then they're basically wheeled out and put into a dry dock, which is then flooded, and that's when they start. Has also all kinds of new design concepts, has a photonic mast, basically. Rather than having a physical periscope operated by hydraulics moving up and down through the center of the submarine and breaching the hull integrity, it now uses an electric power and fiber optic cables. The reason for that is that anytime you have a penetration of the hull, and that periscope tube was one of the largest penetrations of the hull, that there's a source of water coming in. If we want our submarines to dive very deep, we need to eliminate any potential source of failure. And so this allows now, you can see the captain on the right-hand side, he's got a joystick and is basically looking at it on a flat panel. So no more captains hunched over periscope like World War II movies. Instead, it's now done electronically. Virginias also have some other interesting innovations. Instead of a traditional propeller, it was called a pump jet propulsor, you can see there on the back of the submarine. That makes them much quieter. It's a shroud, keeps it quiet, also makes it much more, it prevents cavitation, other kinds of conditions that give noise out into the ocean. As I mentioned, they're multi-mission platforms, so they're not simply dedicated to sinking other enemy submarines. They have Tomahawk missiles for land strike. They have anti-submarine warfare, the Mark 48 torpedo. They have anti-ship weapons, Tomahawk and Harpoon missiles. They can drop mines. They can do covert insertion, dropping SEAL teams ashore or near enemy coastlines and so forth. And again, similar to the permanent class, they have tremendous electronics for intelligence gathering, for intercepting radio communications and so forth. And that brings us to our conclusion. That's how we got to where we are today. As you can see, it's not been a straight line. Navy's done many different diversions, but over the course of 50 years, have learned lessons, took new design approaches, and put them into submarines that will provide us with that technological superiority which we need today. So thank you for your time. I hope you enjoyed listening to the presentation. I apologize for going too quickly in some cases, but thank you for your time.